Hi, this is Mrs. Mendy, and today we're going to go over some of the basics of what is science. Science is both a way of finding things out and the things we find out. Survey, we're going to try doing this. So pause the video here. The way of finding things out is the scientific method. With your science fair project, we're learning the scientific method. That's why we're doing it. The things we find out are stories about how the natural world works. For example, what we know about the Zika virus, which is a virus that was pretty dangerous several years back. And here's some things that we know about it. Zika is spread mostly by the bite of an infected mosquito of a certain species. Zika can be passed from a pregnant woman to her fetus or her unborn baby. Infection during pregnancy can cause certain birth defects, and those birth defects are pretty bad. So if here is a regular baby with a regular baby-sized head, a baby who had been infected with Zika while it was developing could have a much smaller head or an really crazily smaller head than a regular head size. So these are very severe birth defects, and you cannot come back from this. So that's a story that is the kind of story that we care about in science, all kinds of different things, but that's a big one. To ask scientific questions, they're not just like regular questions. Science asks questions you can answer using objective data. And I underline that because that's like a vocabulary word. You will need to know what objective means. So objective data are facts that are about the same for everyone if people find them in the same way. So examples of objective data are measurements of length, weight, speed, any other kind of straightforward measurement like that, counting things, or observations of places or things. These are things that if multiple people do them, they're going to get the same answer. They're not really things that people argue about, not in the same way, because you may be a little bit off one way or another, but there's really a correct answer. So you have to be able to agree that certain things are facts to be able to do science. So for example, many people said that Trump's inauguration crowds were bigger than Obama's, but that's measurably not true. So if someone can look at this and say there are more people here than here, then we cannot do science with those people because they will just ignore facts. So you have to be able to be willing to something, I don't know what happened there, that something is a fact, it is measurable, you can check it. You can see, is it right or is it wrong? Okay, and that is not true. No matter what you feel politically, that is not a true statement. Another survey. We'll try and see if this works this time. So pause the video now. Okay, as powerful as science is, not everything can be answered with science. There are some kinds of data that are different for different people, and yet no one is wrong. So that's different than the objective data where they're just set facts. And if someone messes that up, they're just wrong, it's incorrect. So subjective data are data that are different for everyone. So some examples of subjective questions: which ice cream is best? Which religion is best? I mean, lots of people would have different answers for that, and there's no way to objectively say that one is better than another. How did you feel yesterday? That only you know. What career should you have? That is going to be different for everybody. There's not like a right or wrong question that you can correct somebody on. A really great thing about science, and the core wonderful thing about science, is that scientific thinking catches lies and mistakes. We may be wrong, but we're not going to be wrong forever because the scientific method scrapes away at things that are wrong over time. However, a weird thing about science and a thing that freaks some people out is that it's always changing. And that's because it catches lies and mistakes. It's not because it's wrong or because it's bad, it's because it's about the nature of knowing what we know. We have incomplete knowledge, so our conclusions change as we know more. And there's an old story about blind men going and investigating an elephant. And they crawled all over the elephant, and each of them felt a different part. And so the one that felt the tusk said, it's a spear. And the other one that felt the trunk said, no, it's a snake. The one that felt the leg said, it's a tree. The one that felt the side said, no, it's a wall. I can feel it. And the one that felt the big flappy ear said, it's a fan. And the one that felt the tail said, it's a rope. Now, all of those people took good data. They made good observations. The only thing is they didn't have it all. They didn't see how all of those things went together. So of course, your conclusions are going to change if you don't have all the data. So none of these people are wrong. They just don't have all of it. So our conclusions would have to, of course, change as we know more. Some people don't trust science because science, the stories part of science, is always changing. For example, it wasn't always clear that cigarettes cause cancer. But that's because what we can measure is always changing, and what we have measured is always changing. Science gives us the best answer with the information we have. So once people studied this and said, okay, no, this is really inappropriate for this doctor to be in this cigarette commercial, okay, because the connection between cigarettes and cancer was made much clearer to everyone. Hypothesis. A hypothesis is a really important part of the scientific method because as Buddy from Dinosaur Train knows, if you have a hypothesis, you have an idea that you can test, says Tiny. So it can't just be any old idea. It can't just be an educated guess. It has to be something that is testable. It doesn't even matter if it's wrong, so long as you can test whether it's right or wrong. That's really what matters. If you have just a regular question and you want to change that to a hypothesis, you have to make the question very specific, very focused in. So for example, if a question that you want to ask is, what do squirrels eat? The hypothesis, or a hypothesis that you can make, an hypothesis, I suppose, would be, do squirrels in my neighborhood prefer peanuts to sunflower seeds if both are there? So you can see that this is a really focused idea and is very narrow, and it just deals with the experiment that you are actually doing. It's not everything about what do squirrels eat. It's just saying, of the things that squirrels eat, do they like this one better or this one better if I offer them in a certain way? The methods part of an experiment is really important because it says how you did your experiment. Now, how scientists actually do this, real scientists, is they will say in a narrative form what they did. And so I'm going to make you guys do that to practice being scientists. You're going to write what you did in enough detail that someone else could repeat your experiment perfectly. So that's going to be a lot of detail. You're going to roll your eyes at me. That's just how much detail it's going to be. But the format that I want you to have is to start thinking of yourself as a scientist, saying like, I measured the voltage of 6 batteries using a voltmeter. You don't have to use these instructions like somebody told you how to do this, okay? That's what you do when you don't know what you're doing. You just follow somebody else's directions. And the idea here is that you're saying what you did and in enough detail that you don't have to have a list. You don't have to have 1, 2, 3, 4, okay? So this is the format that I want you to try to practice. In every experiment, there are going to be variables, and a variable you may remember from math, if you've had this already, that a variable is something that changes. It varies. In experiments, you'll have an independent variable. That's the part that you change. That's when you're deciding, what you're going to change about your two groups to make your experiment. The dependent variable, that's what you observe. That's what you don't know before you do the experiment. Okay, that's what you're expecting to change when you change the independent variable. And then a controlled variable, that's what you keep the same. So everything between your two groups that you're testing should be exactly the same, or the two situations, whatever, except they'll vary by the independent variable. Okay, that's the thing that's different between your two test groups. So for example, in our little squirrel experiment that I just is hypothetical, what food do squirrels like best? The independent variable for that, the thing that you change, think about what that is for a second, and I'll give you a second to think about that. So what is that? That is the food type. Okay, the independent variable, the thing that is different is you're offering this thing and you're offering this thing. Okay, sunflower seeds and peanuts. Now, the dependent variable, the thing you observe, the thing you don't know, it's going to be like the results of your experiment. And the dependent variable will be how much food is eaten. So of which kind, how much food is eaten, or you could make it, which one is eaten first. That could be the dependent variable too. It depends on your experiment, what it is. Okay, but one thing you know beforehand, because you set up the experiment that way. The other thing you don't know. You're asking the universe how much food will be eaten. You don't know beforehand. Why you care about this? Well, besides that you think one thing it will be affecting the other thing, it will depend on which axis it goes on your graph. So the independent variable usually goes on the x-axis. And then the dependent variable goes on the y-axis. So this is the thing that you know is how it's going to be, like what numbers are here. You don't know what numbers are going to be here. In your results, that will be a section where you report what you found. It's what you saw in your experiment. And the format of how you do that is you will have text, words, describing your data, like sentences saying what your data are from your experiments, and at least one graph. Now, will the text say the same thing as the graph? Yes, it will. It will say exactly the same thing, but it's showing it in a different way. In your conclusion, you're going to restate your hypothesis, accept or reject it, depending on what your data said, and say what future directions, like what you would do if you were going to do this experiment again. That was a long one. So that's it for today.